starting off our study of electricity in Unit 1 for Year 11s, looking at charge. So there's two kinds of charge, and the source of those different types of charges are protons and neutrons. So not neutrons, electrons. So you've done this in junior science. You know that the protons and neutrons are in the centre, and then we have these orbitals around the outside where the electrons like to hang out. So that's a recap. And also you should remember from junior that the size of a positive charge and the size of a negative charge is the same. So that overall, when you've got the same number of protons and the same number of electrons, the atom's neutral. Right? So charge is measured in coulombs. That's named after the scientist Charles Augustin de Coulomb. And because it's named after a scientist, it gets a capital letter, it gets a capital C. 1 coulomb of electric charge is equivalent to the charge on 6.25 by 10 to the 18 electrons. And that actually is a pretty significant charge in real life. So if an object's got extra electrons, it's going to have a negative charge. If it has a lack of electrons, it's lost electrons somehow, and you've all done the rub an object with a piece of cloth like a comb or something like that where you've built up a static charge. So if it loses electrons, it's going to become positive. If it gains electrons, it's going to become negative. And there's a conservation of charge, and it says that the amount of negative charge gained by one is equal to the amount of positive charge left on the other, so that charge is conserved. So you end up, if you added them together, you'd end up with 0. Right, over here there's just a little calculation here about the number of elementary charges, and an elementary charge is the charge on an electron. So the number of elementary charge is the total charge divided by the size of the elementary charge. That makes sense, doesn't it? So there's an example. We've got calculate the number of excess electrons. Does it make it easier? Oh, it does. In a charge of 2.5 coulombs. So you divide the 2.5 by the size of the charge on an electron, and you find out that there was 1.6 by 10 to the 19 electrons. So that's pretty straightforward. Capital Q for total charge, small q for the charge of an electron. Right, over here, conductors are usually metals, but the thing that they have in common is that the way that they're bonded, these electrons are free to move around. So that's how they're able to carry the charge. Insulators, the electrons are more tightly bound and the charge doesn't pass through. Right, and now we're on to current and voltage. So that's just a bit of background about charge. So voltage is a measure of electric potential energy per unit charge. So that's the amount of energy the electrons have. So you can have super energetic electrons or you can have tired, sluggish electrons. So voltage is a measure of the amount of energy that the electrons have. And so it varies in our daily usage. 240 volts is your electricity for your house. 12 volts is your car battery. AA battery, 1.5 volts. Volts is again named after a scientist, Volta. So it gets a capital V. So voltage is measured in volts, capital V. Current is the flow of electrons, like how fast electrons are flowing. So if you think of a garden hose, is the water flowing out slowly? Is the water flowing quickly? So that's an analogy with current, and you can think of water has currents, electricity has currents. It's a flow, it's a rate. It's a rate of charge moving through. And so because it's a rate, you can work it out by dividing by time. So the current gets a capital I. Why it's I don't know. Guess because C was already taken. It's the amount of charge divided by time. So charge per second. And the unit for it is the ampere. And again, Ampere was a scientist, so it gets a capital A for the symbol. So 1 ampere of electric current is a flow of 1 coulomb, a charge of 1 coulomb per second. So 1 amp is 1 coulomb per second. So that many electrons per second flowing. And again, 1 amp is fairly large because I said to you before, 1 coulomb is a fairly large amount of charge. So 1 amp is quite large as well. All right, it says here household appliances typically use up to about 20 amps. So light uses 0.25, microwave uses 3, stove 15. You're not going to get much above that. So it's common then, because these are fairly large amounts, it's common for us to be measuring amps in microamps or more commonly still milliamps. So small m in front, that small m means by 10 to the negative 3, it's thousandths. So thousandths of amps is quite common. Right, and you measure electric current with an ammeter, you measure voltage with a voltmeter. So there's a little summary here at the bottom of the page. We've got electric charge is capital Q, current is I, coulombs and amps. All capitals, that's handy. Little example here, if we've got 30 coulombs of charge passing in 1 minute, that's in minutes. We'll need it in seconds. So 30 divided by 60, 0.5 amps. Right, and then this one here is pretty straightforward rejig of those couple of formulas. Righto, there's a couple of different sorts of current. Something to realise early on is that when we're doing circuit diagrams, we use a thing called conventional current. When they first were learning about this, they thought that the current was being positive charge moving. So in a circuit diagram, they always mark the current as going from the positive round to the negative. That's the way a positive charge would go. It would be repelled from this positive electrode here and go around the circuit that way. So that's called conventional current. We know now that it's the electrons that are moving, so the current is actually flowing around this way. It doesn't really, in the scheme of things, make much difference because current flow is instantaneous and the effect on the light bulb is going to be the same whether the current's going that way or the current's going this way. It's just something to be aware of. And it's something that's never been changed. I don't know why they didn't go, oh, now that we know better, let's mark the current this way. But they haven't. They've stuck to it and they still mark current as flowing from positive to negative. So that's annoying. So over here in this diagram, you can see straight up, they've got the current flow marked in as flowing from positive to negative, but we know it's not. This is just a little analogy for current, and it's like a water pump. So this would be a battery that's putting the energy into pushing the current. The current is the flow of water. This turbine here is going to use up some of the energy. That's going to be like a light bulb or some sort of appliance, some kind of resistance that's going to use up the energy. We've got a water flow meter here. That's the ammeter. So ammeters get joined into the circuit where you want to measure the current. We'll get on to voltmeters later on. They're joined across. So you would join a voltmeter up, over and down, or if it was here like this across the current, across the circuit that the circuit element that you're trying to measure. But an ammeter goes in the circuit. So this is an analogy for direct current. Direct current only flows in one direction. This is a sort of thing that you get from a battery. It is not your household electricity. In your household electricity, it's an alternating current from a generator that's going round and round. So it actually makes the current go backwards and forwards. So if you were watching it here, you would see it go one way, turn back, go the other way, turn back. And so the current would go like that. But if you use, this is direct current, it just stays constant the whole time. So alternating current is what you have in your house. It's from a generator, like a big turbine at the power station, and the current is continuously changing. Whereas direct current, it stays the same all the time. All right. And then again, I'll just try and get a better angle. There we go. I mentioned before, the ammeter gets connected in series. It's measuring the current in this circuit, and it doesn't matter whether you put it here or put it here or put it there or there. The current is the same. The water flow is the same all the way, or the electricity flow, the water flow, if you're thinking of that water pump situation before, it's the same all the way through. So it doesn't matter where in the circuit you place it. Analog ammeter, you'll see them in the cupboard up the back of B6. I'm a bit overusing them. I think we've got plenty of multimeters, which will give us a digital. And when you read this, you always have the element of human error. If you're not directly in front of the needle, you'll get parallax error. So the reading will be slightly off. Lots of these sorts of instruments actually have a little mirror strip that runs along here, and the idea is that you get the needle and the image directly on top of each other so that you know you're directly in front of it when you take your reading. And they have 2 scales usually. That one there's got 3 actually, but this has got 3. Depending on which one of these you hook into, it depends on which scale you're reading. But yeah, we'll just use a digital. We'll do that for your basic introductory experiment so that when you go to do your student experiment, if you're doing an electricity one, you can immediately refine it and use a digital meter. So that would be one of your refinements to get rid of that human error.